At this point, we're going to start discussing turbulent boundary layers, and we need to use a little bit different analysis method to solve for the behavior of a turbulent boundary layer. Now, turbulence usually occurs over a region. Typically, we assume that transition to turbulence occurs at a Reynolds number of about 500,000. However, we can actually trip the flow to initiate turbulence at almost any Reynolds number. For instance, we could trip the flow at the leading edge of the plate, where x equals 0. And then the flow over the entire plate would be turbulent. There would be no laminar boundary layer region. We can also delay the transition beyond this Reynolds number. If the plate is designed to be very smooth, we're very careful to make sure the inlet flow doesn't have any perturbations, things like that. We can cause the transition to turbulence to be delayed to much higher Reynolds numbers. There are also some important features that we can look at when it comes to turbulent boundary layers. Basically, from experimental measurements and observations, we can see that turbulent boundary layers have much steeper velocity gradients near the wall. This means there's going to be higher shear, so the skin friction coefficient is going to be higher, and there's going to be more drag force. We can also see that because most of the fluid is moving faster, we can look at the momentum flux profile and see that the turbulent boundary layer has much higher inertia than a laminar boundary layer. And these features are very important. Turbulent boundary layers have more mixing. So the boundary layer is going to grow faster because it's easier to transfer momentum from one location to another. We already talked about larger drag. There's also can be increased heat transfer. And the increased inertia of a turbulent boundary layer means that it's harder to slow it down. And it helps turbulent boundary layers resist boundary layer separation better than laminar boundary layers. Unfortunately, we can't solve these equations directly. Instability due to turbulence prevents solution methods like the Blasius equation, and so we need an alternate method. And our alternate method is the von Karman momentum integral. This idea is intended to provide a general solution for all types of boundary layers, and it's based on this control room method, or control volume method. So we start by looking at our control volume, and we look at mass in and mass out. And we look at momentum in and momentum out, and we balance this with the drag force. So we're going to assume a 2D steady incompressible flow, and the result of this analysis comes up to look something like this. So here, tau W is the wall shear. Basically, it's mu du dy at the wall. And it's also important to note we have the momentum thickness and we have the displacement thickness in this equation. So because of this, there's some important things we need to talk about. Now, it's important. This equation is an ordinary differential equation for the boundary layer thickness, so it's easier to solve. And the method is very general, but there's one major shortcoming, and that is that we need to know the velocity profile. Velocity divided by free stream velocity in order to find the boundary layer thickness, because we need that quantity we need to know little u over capital U in order to find the momentum thickness and the displacement thickness. So the solution procedure is going to be to first obtain an initial guess for the free stream velocity from a potential flow theory. Second, we need to assume a reasonable velocity profile in the boundary layer. So it's not from any theory, it's basically an assumption that the velocity profile is similar to this function, whatever that function is that we choose. And then we need to assume a reasonable model for wall shear, and that can either be from Newton's law of viscosity, from our velocity profile that we've assumed, or we can use some empirical correlation based on experiment. And from that, we solve the von Karman momentum integral to obtain an expression for boundary layer thickness. Now, if the boundary layer is thick, we may need to iterate by going back and obtaining a new guess for the free stream velocity from potential flow theory. Now, we can demonstrate this process for laminar flow. We're going to assume a simple case, and that simple case is that the free stream velocity is constant. So we have a flat plate in an infinite or semi-infinite region. So if the free stream velocity is constant, then du dx is 0, and we no longer have to consider that second term. So that's going to simplify our math. Then we need to choose a velocity profile. Now, the Blasius solution doesn't have an analytic form, so we can't use the Blasius solution. However, we can try other options. We can look at quadratic, cubic, logarithmic, or other forms. We're going to start by just using a quadratic form. It's very simple. Now, this is reasonable. There's zero gradient at the boundary layer thickness, where y equals delta, and so on. So we can actually then go through and derive the next step, the wall shear, based on Newton's law of viscosity. So now we have a velocity profile and we have a wall shear. So then we can go through and use the equation for momentum thickness to come up with a function that depends on delta. And we can solve the equation for delta over x to come up with our model for boundary layer thickness. Now, we can note that this gives about 10% error compared to the Blasius equation. And the reason that this gives us a little bit of error is because our velocity profile was pretty simple. However, we can use other velocity profiles to give us better approximations for the boundary layer behavior. Now, turbulent flow is a little bit more difficult to analyze. We start with the assumption of a 1/7 power velocity profile. Now, this is a very common velocity profile for analysis of turbulent flows, and it gives us a pretty reasonable approximation for momentum flux, or the inertia of the boundary layer. However, it's not as accurate for certain other parameters. For instance, we cannot use this to calculate the wall shear. Using this equation, du dy is going to be essentially infinite at y equals 0. So we can't use this velocity profile to find the wall shear. Instead, we use an empirical model. And this empirical model is developed based on experimental data and a pipe flow model. So keep in mind that this is also an approximation. So now we have an approximation for wall shear and an approximation for the velocity profile. So once again, we're just going to analyze a flat plate. So the basic assumptions are the same, and the final equation is going to be the same. We've just changed our velocity profile for the definition of theta, and we have a different expression for wall shear, tau w. We also have a problem with our boundary condition, where we start, delta at x equals something. Now we're going to analyze this case by assuming that turbulence is tripped at the leading edge of the plate. So delta equals 0 at x equals 0. And then the whole thing is turbulent. When all is said and done, the model gives us this result. So we have now a model for delta over x, skin friction coefficient, and drag coefficient. And you'll note that the model for the boundary layer thickness is proportional now to Reynolds number to the 1/5 rather than Reynolds number to the 1/2. So this solution results in equations that are much like the Blasius method for laminar boundary layers. However, it's important to remember that this model is an approximation that's based on some key assumptions, and it needs to be compared with experimental data to validate its performance. And we can do that by graphing it. Now, mixed boundary layers start as laminar, and then they transition to become turbulent. So the math in this case is more complex. We use the laminar boundary layer model to provide a boundary condition for the turbulent part. So for the laminar part, we use the Blasius solution, and for the turbulent part, we use the momentum integral equation, and we have a boundary layer, or a transition. So the initial condition for our turbulent boundary layer is the laminar boundary layer thickness at the critical Reynolds number of about 500,000. And when we do the math, we find out that the drag coefficient can be expressed as a function of Reynolds number, and then we have an additional term for the critical Reynolds number, 1,740 over the critical Reynolds number. And we can actually display this graphically, where we have the Blasius solution here. We also have the turbulent boundary layer approximation from the 1/7 power profile, and then we have this dashed line in the middle that shows the behavior for the mixed boundary layer. And we can develop a model for that transition.